In this video, I'm going to show the image of why we need a power integrity PI analysis with the IRdrop in a circuit system, especially in the chip or on the die. As we know, with the advanced technology, the supply voltage has decreased quite a lot, especially the core or digital supply voltage for the core or digital device. Therefore, the low supply not only slows down the digital gates, but also degrades the headroom of any analog circuitry, such as amplifiers. To make sure both digital and analog circuits work properly as expected, we need to make sure the supply voltage don't be reduced to any unexpected value to break or clog the digital timing or the analog behavior. That's why we must do the on-die power integrity PI analysis, which is the IRdrop analysis, since it's quite critical in any SoC system, including the circuit system. Most industry tools like the Red Hat of ANSYS, Voltus of Cadence design system. But why would the on-die IRdrop be so much more than what you expected? First of all, what's the IRdrop? Correct. The R would be the resistance of the metal routing. Metal layers used in power, VDD or ground, routings or grid should have finite resistivity or resistance. Then the I would be the current flowing through the metal of those power grids, which is also called Power Delivery Network, PDN. Therefore, the voltage drop may come from the current I times the resistance of the PDN, and we call IRdrop since again V equals I times R. If this IRdrop a DC value of an AC value, think about the current flowing image for 5 seconds. Bingo! Both. As we know, any current would include a DC current and an AC current on top of it. Even though the resistance should be static, the current would have both DC and AC components. Therefore, any type of IRdrop would be static DC and dynamic AC IRdrop for sure. After understanding the types of the IRdrop, we could verify each type of IRdrop and then try to improve or decrease the IRdrop, respectively. Let's start with the static IRdrop. What can we do if we see the static IRdrop is too much? Think about the resistance image for 5 seconds. Correct. We cannot reduce the DC current of the circuitry, and it's likely due to the resistance being too much. What should we do? Think about the metal resistance images for 5 seconds. Yes, a bigger cross-section area or a shorter routing length should decrease the resistance. What's further? Right. First, you could make the metal strip wider to increase the cross area or reduce the resistance. Second, you could increase the height of the metal strip by pairing a few metal layers together to increase the cross area or reduce the resistance. Third, you could add more branches to reduce the length of the current flowing such that the resistance is reduced, which is usually a good metal mesh or grid in a good design of the PDN. Alright, usually the static DC IRdrop could be easy to improve. What should we do if the issue is the dynamic IRdrop? Bingo! The dynamic IRdrop must come from the dynamic current, which happens when there's an increasing of drawing of the current from the power supply because of the switching activities on the chip. Therefore, we must reduce the dynamic AC switching as much as we can. But how? Think about the filtering images for 5 seconds. Correct. If the high frequency AC switching current caused the big IR drop, we could provide a low impedance path by adding the capacitors, which filter the high frequency noise in the current and should reduce the voltage drop a lot. But the decoupling capacitor must be placed close to the supply and ground connection of the transistor to filter out those switching ripples effectively. In addition to the decoupling capacitor, can we reduce the dynamic drop further? Think about the impedance images for 5 seconds. Bingo! The dynamic voltage would be L times di dt. Therefore, we must not only reduce the di dt by adding the decoupling capacitor, but also reduce the inductance. Since the chip dimension is quite small, the inductance won't be too big, but the chip's package would add quite a big inductance here. Therefore, in the past, the chip package of the QFN wire bonding could result a big inductance, which is probably okay for the series of data rate less than 3 or 4 gigabit per second. But for the higher data rate up to 8 gigabit per second, we may need to increase the chip package cost a little through a free chip wire bond, which would reduce the wire bond inductance quite a bit. Unfortunately, for high-speed series of data rate greater than 10 gigabit per second, we must pay a much higher package cost with a free chip BGA, which will almost eliminate the inductance a lot. Again, the chip package would relate to the cost and performance trade-off. We will just briefly mention it here, and we can talk about the types of package later if anyone is interested. Alright, instead of the IRdrop optimization, what else we could do if we still cannot mitigate those big current spikes from the tremendous digital circuit switching events? Think about the isolation images for 5 seconds. Correct. The analog supply is usually quiet for most amplifiers, but the digital supply is quite noisy and will further couple to the analog circuitry and crop the normal operation. To avoid that, we must isolate both analog and digital supply to avoid the noise coupling. Again, for some circuitry tied to the analog supply like the TX output driver, we must also put as much decoupling capacitor near the supply pins of the switching transistor as close as possible. But for those digital circuitry, what can we do for those big voltage drops, which could cause timing variation, setup, and hold time? Think about the DFS image for 5 seconds. Right, you should apply the dynamic voltage frequency scaling technique to switching the clock to a lower frequency, while the digital supply drops a lot. We will describe why DFS is in detail, and I will let you review it. Feel free to let me know if you have further questions. Here is the summarized image of why we need a power integrity PI analysis with the IRdrop in a SerDes system, especially in the chip or on the die. Intuitively, if the supply voltage drops too much, the transistor will not turn on well. Therefore, in digital gates, a low supply will either slow down the clock path or the data path in a flip-flop system to result in a timing variation, such as the setup or hold time variation. But in analog blocks, a low supply voltage will consume the headroom of any current source in biasing or amplifier to cause accuracy degradation. Therefore, we need to analyze the IR drop carefully and mitigate the voltage drop in several ways. First, we need to reduce the static supply voltage drop with a bigger cross-section area or a shorter routing length by making the metal strip wider, pairing a few metal layers together, and adding more branches to reduce the length of current flowing. In summary, we need to make sure to keep a good metal mesh or grid in a good design of the PDN. Second, we need to reduce the dynamic IR drop by adding more decoupling capacitors close to the power and ground connection of the transistors to fill out the switching ripple effectively. In addition, reducing the chip package lead inductance with a higher cost, like a feature BGA, will vary effectively. Third, a dedicated analog supply for the biasing or the amplifier will prevent the noise crosstalk from the digital supply back from the digital gates. To mitigate the digital timing variation, we still can add the DVFS approach to keep both timing and performance at the same time. Lastly, to sign off the IR drop verification, luckily, we have either the Red Hat of Ansys or Voltus of Cadence design system to help you. Please be advised that I just provide the tool information, but do not promote or sell any tool to you. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.